All right, folks, welcome to CS61C Lecture 11. We're at the last stage of talking about how MIPS converts, how C converts to MIPS. We've seen that before. And today in particular, we're learning about the register calling conventions. So what do you do when you're calling another MIPS call, making another subroutine call with a JAL? What can you trust will be saved? What can you ensure will be possibly clobbered? And those things. In the news of the day, Amazon, you know, has a cloud. Obviously, the Amazon has a wonderful cloud. There's a company called Cycle Computing whose job it is. They've made their job to be an intermediary between you and Amazon, and you say, I want these specs, and they will then make this compute cluster happen. So the cloud is out there, but there are basically a lot of virtualization instances you have to make up yourself individually. This cycle basically says it's all the same. It's all the same thing. It's all the same node. Lots of different nodes, but all the same environment. Makes it much easier to manage that. So what they finally came up with is they came up with this pharmaceutical, one of the top 5 pharmaceutical companies. They call them top 5 pharmas. They said, we need a lot of compute power for this embarrassingly parallel task. And they hired this cycle computer company. And what they came up with is 3809 compute instances, each with 8 cores, 7 gigs of RAM each, for a total, which 7 is a weird number, but for a total of 30,000 cores, 26 terabytes, and 2 petabytes for this one instance. The cost for the whole thing was $1,000 per hour. And that's piddly. That's nothing. I mean, $1,000 an hour, you pay that for like the energy from your own server farm. And that's nothing. And they got this done in a couple hours. It was an incredible thing. Read about this in Ars Technica. But fascinating to me that that's now available to you if you need that. If you have 1,000 hours and you need this really embarrassingly parallel thing, you can make use of an incredible amount of resources through this company. No one has since emailed me if you're listening remotely, so if you're watching the webcast and you want to shout out, please email me, ddgarcia@csberkeley.edu. In review, we have seen now a ton of different things, arithmetic ops, some memory ops, decisions to be smart, some branches, and unconditional branches. I'm a little hot on the microphone. Bink, bink. We've seen all the registers now. You now know you guys are almost ready to do anything. The only thing you're missing is, if you're going to be making a function call, if you're going to say JAL something, what can you trust will be clobbered, or might be clobbered, and what can you trust will be saved? So that's what today is about. But I wanted to talk about memory before, because this is now, we kind of leaked in this, and it was a really nice lecture where we tie in, where you're finally making use of the stack, and making use of the heap, and you actually know what those pieces are. We didn't actually talk, let's talk another level down behind that. This is our review. You see the stack as your frames. You now know how to control this. How do you get more memory on the stack? One line, 1 nanosecond or fewer. Yeah, add I, $SP minus whatever you want. Easy. Now you got some memory. Free, fast. Is there a check on that? If you end up having that overlap with where the top of the heap is that something that gets caught in C? No. And that's a problem, right? That is a problem. Anytime you use the stack, the system will just crash on you. There is no way to catch that. If you have a malloc call, you can say, malloc, recall, what does malloc do when it fails? Returns null. You can test it. You can gracefully exit. You cannot verify when the stack overflows. So you cannot reliably guarantee to any user that you won't crash. You cannot reliably guarantee that you won't crash, honestly. You want to try to sell this. You're a company, you're Microsoft. It's never crashed. No, it will crash because there's no way to catch a stack overflow. There's no way to catch that. So if you have enough recursion depth and your heap happens to be grown up to this point, you're going to overlap that label and you're in trouble. In general, the stack stores $RA, which is the return address, parameters, which are any parameters to a function, and also space for local variables. I say parameters to a function because if you have any more than 4 arguments to a function, A0 through A3, you got to store them in the stack to pass it into a function. Okay? So here is the animation. Here's exactly how this works. This is kind of cool. I'm in main and I call A with an argument 0. All these guys are void. So now I need some space in the stack to have A. This is kind of like how you would translate this to C. You'd be moving down to store some whatever local variables you need for that frame of A. To know that after A is done, you got to come back to right below A. So that has to be stored here. So now you're in A, and what A means, you got to bring the stack pointer's there, by the way, and now you're in A, and you grow the stack down to here, and now you have your local variables for A, which might be, M is probably in A0, but you need at least to save RA, because you're going to make a function call in A. You got to remember what RA was in A to go back to where main was. You got to store that guy. And you keep doing this. You keep doing this, right? This is all the same. Bink, bink, bink. You call C. You call D. Now watch this. Here's the best part about PowerPoint. D returns, and the stack frame goes back to there. Does C erase the stuff in, what color is that? Orange. No, your answer is whatever the fastest thing you can do is. Is it faster to erase or not erase? It's faster not to erase. The answer is C doesn't erase then. And you keep going back. And you keep bumping back. It's kind of like a literal stack, right? It's push, 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 pop, 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 pop. If you turn this upside down, it's like the actual stack of dishes. Okay, you keep going back to here, keep going back to there, keep going back to there. That's the idea. Okay, every time you return, you're basically moving SP back up. Every time you call something, you move SP down. That's how it works. And if you have a recursive thing, you're just going to keep going down, 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 down until you hit the end. If it doesn't hit the end, you have a traditional stack overflow, and you keep going. Question there. You had a question. Say it again. What prevents?
What prevents you from keeping track of the heap pointer, and that you could determine if you were going to pass the heap pointer?
The system keeps track of where the heap is. malloc is a function call. It's not yours. Even if you're in MIPS, how do you call malloc? It's jow malloc. Malloc's just a library function that's going to get you some memory and return a pointer. And V0 is the pointer to that uninitialized memory space. So basically, you have no control over malloc. We're going to talk about malloc in a second. Yeah. Well, here's the thing. You do know, if you're making calls to malloc, what the highest point of heap ever could be. But you don't know how much static stuff there is, really, and you don't know how much code there is. So when it's all loaded up, you kind of know what you're doing in malloc because you control that, but you don't really know where that starting point is to know what that additional point might be, really. So you can't ask that question, unfortunately. So here's an interesting point. I love this piece of code. Because people, you know this on the top level, but you didn't actually know the picture. This picture you didn't know before this. Let's take an example. I'm in main. I have two variables, stack address and content. Stack address is equal to the pointer that pointer returns. What does pointer do? It makes a local variable y, sets y to 3, returns the address to that. Already you know that's illegal. We shouldn't do that because that temporary space for y is going to go away. But now you know exactly why that's a problem. Because, watch this, I'm in main, I then call pointer. I move the stack pointer down, I make the frame for that guy, and y lives in that memory below, right? There's the main frame and there's the pointer frame. And y lives in that pointer frame. Okay, stay with me. Now, so stack address equals there. So the stack address is guy up here living in main. He points to the space down there. That makes sense? There's an arrow. The box lives up there. Main has stack address. That's a valid space. That's a box for it. That's a pointer. And it goes down into that illegal area below. It's legal while it's running, but it's not illegal the moment this guy returns. You don't have access to that. That stuff is not there anymore, right? So here's main after pointer returns. You cannot trust what's there. You have no idea what is going to be down there. But watch this. It does return. Remember, I ask you, does C erase it out to clear memory? It doesn't. So, does a 3 still live in that box? In this little hole there? Does a 3 still live in this kind of empty gap there? Yes. Watch this. Content equals star stack pointer. What that does is that goes in, follows the arrow, grabs whatever there, and brings it back into content. Content lives up in main, which is good. So we just basically go in and get it. Okay? So here's a treasure map. Go follow the map and go get whatever's there. And you come back and say, here's what I found, Dan. It's a 3. I'm like, yoo-hoo! How do I know it's a 3? Oh, boy. How do I know it's a 3? I had to call print, didn't I? I called print. %D, content, print's a 3. What's print, by the way? A function. What do you do when you call a function? Uh-oh. Wait, what? You just grew the stack? Oh. I grew the stack. Now I need some local space for whatever print needs. Print has some locals. I don't know how print works. Print's a library function. I don't care about that. But print's going to stomp and clobber all over those good bits that look like they were a solid 3. But guess what happens? All I do is follow that pointer again. The pointer doesn't change. Stack address still points to that same guy. That's the arrow. That line says, follow the arrow, grab what's over there. Remember that question we had before? Can you go to follow this map? Same map. Go grab what's there now and bring it back. Brings it back, stuffs it in content. And now, printf content, garbage. Garbage, people. You see that? This looks like magic. Wait, I did the same thing twice in a row and I get random results? What's happening? As a new programmer, you're like, if you don't know what I'm teaching you today, if you don't know 621C material and only learning an intro to C, which by the way is how they teach at a lot of schools, just here's C, good luck. But they don't teach the machine structures part of it. If you don't understand what this box is, you have no idea why this thing, and there's no way you could know why this thing returns 3 the first time and garbage the second time. There's no way. If you don't understand this behind the scenes, open the hood, 621C beauty. Let's pat ourselves in the back. Huh? Now you do. But now you do, and now you understand that. That's cool. One thing, by the way, I forgot to mention. Remember we saw how we slowly called, it was like, oh, what was it? Something called add. It was like sum squares calls mult. Do you remember that? Sum squares calls mult. And we had to kind of copy x to the second argument of mult. Remember that? So we copied that so that A1 got A0. Do you remember this at all? Oh, so painful. Okay, I wish I had a picture. One of the things I forgot to tell you is, if you want to make your code really slow, let's say you have 4 functions. Foo calls bar, bar calls baz, baz calls garply. Foo has an A, B, C, and D. Let's say you just have four arguments, A, B, C, and D, right? And you call bar, but bar decides to call baz by reordering them. It's now B, C, D, and A. Well, A0 through A3 were all set up to be A, B, C, D. If you reorder the order of these things, you slow yourself down. Because in MIPS, you have to reassign what A0 through A4 is. If you keep this order, the parameters in the same order, if A is always in A0, if B is always in A1, if C is always in A2, if D is always in A3, and they call foo, calls bar, calls baz, calls garply in the same order, you can just say jowl, 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 jowl. But if you reorder them, every time the parameter is in a different place in the argument list as it was in the previous guy, you need to be moving that. There's time taken to move them over to the different A to make it work. That kind of interesting? So think about that as you're writing C. This is now advice for a C programmer. This was advice for a C programmer. Don't do this kind of stuff. And another advice is to make your code as fast as possible. Look at the ordering of your arguments, and something that you're going to use a lot, put it first in the argument list, and keep it first. So that as you're moving around, it doesn't have to keep moved around. That makes sense a little bit? I'm trying to help you guys be better programmers. All right. So, memory management. You don't touch code and static. It's done for you. Code is big. The system does that for you. Static is big. System does it for you. Stack frame is easy. We saw how to do that. Okay? But the heap is tricky. You don't do this. You don't have to worry about it, but you are managing it in what you call to malloc. If it's, let's say you need 1,000 bytes. You could either make 1 request for 1,000 bytes, or 10 requests for 100, or 100 requests for 10, or 1,000 requests for 1. Which is better? Well, let's look at it and see what happens. So, what you don't want is memory to be fragmented. Okay? Fragmented memory is going to cost you. Fragmentation means all your open, remember, malloc promises that it gives one contiguous free region. So it might be the case that malloc looks into its free pockets and has enough memory, but just not in the one contiguous free region that you need it to be. Okay? So sometimes malloc will fail if you don't manage memory well. Also, sometimes you can make calls to a system and mallocs and frees. Dan says you got a free whenever you malloc. Mallocs are free, mallocs are free, to end up putting these holes in the structure. Let's look at an example of that. First request is for 100 bytes. Bam. Next request is for 1 byte. Bam. Next, you say, well, Dan said I got to free it if I don't use it. So you use R1, and you're done with R1, and I free it. Bam. Look what you've done. Now look what you've done. You have fragmented your beautiful memory, which looks like it's about 140 bytes high. You can now not serve a request of 139 bytes. If you had done the 1 first, then the 100, the 1 would be on the top. You free that, there's my 139, I can still do 139, but now I cannot. You say, hey Dan, can I get some memory for 139? Nope, sorry. I only have 100 and a 39. Sorry. So, look at the pieces here. Memory has become fragmented. We obviously know that, how does malloc work? And guess what? If you had taken this course more than a year ago, so spring of 10 or before, you would know how malloc works, because we're going to open the hood on that and tell you one implementation of how you could work malloc and how you could be fast and optimal, all that stuff. Here's the one-sentence answer, what we taught you in that lectures. Here's a list of all the free things. It starts with one object. It starts with one item. It's called the free list. List of all the things that are free, just one thing. Points to a region of 140. Now you're here. So now you erase the 140, and now you say I have free of about 40, I guess, here, right? So now you do this, and now it erases the 40 and makes it 39. I still have one free area, right? Okay. Now you clear that. Now that 100 clears out, so now I have two areas. Does that make sense to the linked list? Two things. One points to 100, one points to a 39. Okay? Just as the simplest way to do it, right? No hard data structure, just two guides. The list of all the free areas. What does a list mean? Linear search. Linear search is the slowest thing we can do, right? Literally look through every single one. So as this becomes more and more fragmented, or as your hard drive becomes more and more fragmented, I say, I want some contiguous. The nice thing about hard drives is I can split files up into different things. But in terms of malloc, I have to give you one continuous region. So I have to now search across all of my linear list of things to find a free region that's free. And there's a lot of ways you would go to do this, and whether when you find a space, do you find the space that best fits it, that is the most snug fit, or do you just find the first one to do the next one? All that stuff we're not responsible for anymore in 621C. You used to be. In fact, if you look at the oral exams, I would ask you questions about first fit versus next fit versus best fit, the malloc algorithm. We don't ask you that anymore. That's below the level of abstraction. We say that's malloc's problem. Somebody else has written that somewhere. But there are issues of how you would try to optimize malloc. Okay, but you're not responsible anymore for that here. Just understand that you kind of have to manage memory, the heap, in how you make calls to malloc, and whether it's clean to call it all up at once, and then the stuff you're never going to free, just do it first, and then you'll just never free it. And the stuff that you are, free it later, and that'll be easier. That keeps kind of fewer free regions. Just know that your code is going to have some effect on what the free regions are and how long it takes malloc to work. If I say malloc is not instantaneous. If I say int a of 100, instantaneous, because you know that int a of 100 becomes add I sp minus 400, right? A jow malloc may take you a long time, may take hundreds of instructions, of cycles. One instruction is a jow malloc, but 100 cycles as it goes to his list, and malloc is now going, wait, he wants memory. Okay, now, nope, is it as big as this one? Nope, okay, he wants 1,000,000. No, are you 1,000,000? No. And as it's going to its free list, seeing if everybody is 1,000,000. You see that? Really slow. Malloc can be slow. And if you have a high-performing piece of code, that's going to cause trouble. Then again, malloc is the only way to be able to recover if you don't have the space. And int a of 100 is going to just fail and crash your code. So there's a little bit of a trade-off whether you use the local array in stack or whether you use malloc. All right. So let's do a halfway check-in now. How are you guys doing on the project? Let's kick it in. And let's even give you a free display. Bam. Free display. Hit it hard. Bam. Go. Give me some love. E. Come on, E. Come on, E. Okay, so now what this is telling us, by the way, just I don't know if you realize, but you are telling us a message. What you are telling us is that we give you a 2-week project, and you don't start until a couple days into the second week. Am I right? Isn't that a message? Okay, so from now on, take the 2-week projects, make them all a week, and then, no, I don't know. I'm not doing that. All I'm saying is, I think you should have more A, B through E's. That's all I'm saying. I'm just saying. Okay. All right. And who knows about the... By the way, we had 3 people in the class. Who knows about the other 130 who don't even have their clickers to vote in how many A more... imagine 130 more people in A, right? Very good. Okay, good stuff. TAs, any updates? There was a lab canceled or a power shortage this morning at 8 o'clock. Satarjadai had a new generator. A scheduled facilities update on Satarjadai Hall. But there was an 8 a.m. lab, though. Yay! So the 8 a.m. lab just made it happen. Thank you. Good job, dynamically thinking people, not statically thinking people. Good job. Other issues from students? Just a quick check-in. Yes, in the back. Raise your hand. Go.
Can I ask a question about the stack?
Sure. Question about the stack. Go.
Before you push anything to the stack, it always makes room by incrementing a stack pointer. It seems like you would never put anything into the top or the bottom of the stack instead of down up.
So there was a question about if you have the stack and you always have room. So here's SP. It points to the bottom. If I need, in the example before, I need two words. So I'm going to decrement stack by 8. This is minus 8. That makes 2 spare guys. And now I store one thing in store word $RA $0 SP, and then RA goes here, and $4 SP, and that goes here. So it's just exactly right. It's just exactly right. Minus 8, it just exactly works.
So you never end up putting anything into a 0 spot.
Yeah, here's 0. 0 SP, that's what this is.
But the 0 is also where the stack pointer is.
Correct.
Consider the stack an index array starting at 0. You never put anything in that top box. You always decrement by.
No, even if the whole thing starts, here's the stack, nothing at all. If I want to put one thing in there, I'm decrementing by 4, and it goes to the bottom here, but this is the topmost word, so it will still store the topmost guy. You're fine. It works. Okay, so this is the fun part. So now let's talk about, by the way, the answer here was E. Okay. So let's talk about calling conventions. We talked about how one function foo might call another function bar. We saw A calls B calls C calls D. What are the conventions about what can I trust of my 32 registers to be preserved across the call? I'm going to have some work that I'm doing in my local caller. I'm the caller, and there's the callee, the guy receiving my call. Okay? So what can be changed and what can't be? So in green are the things that are saved. Saved is good. Green is, in this world, good. Okay? Like go. $0 never changes. Yay! That's one off my list. Okay. $S0 through $S7, at the S's, are called S registers for a reason. Now you know why we call them S, or saved registers. It means that I can store some local stuff there, and as I call my subroutine, Zhao, whoever, Zhao, manj on all the registers you want to, as long as they're in the calling conventions. That's my new function name. When it comes back, my S's won't be touched. That's a promise. That's the register calling convention. You can violate them, but you run the risk of not working with any other code that's playing nice with these conventions. Okay? So S's are always saved across a call. By the way, this came up in office hours. People kind of got stuck because they didn't know this. That was kind of fun to push you that way. And SP, you can change it, but again, you got to restore it if you do change it. Because we saw that last time, right? I'm going to go back to my memory and try to get my RA, my own RA and my own A1, SP better be the same SP, because that's otherwise it points to somewhere else. That makes sense. And guess what? Everybody's saved starts with an S. Ha-ha. Isn't that nice? So easy to remember. SP or $S is the only guys that are saved. The only page. 0 and the S's. Uh-oh. You know what that means? Everything else is volatile. Volatile means you can't trust it. Could die at any second. Okay? So RA can change, and in fact it will change. Okay? That's why you have to save RA if you're going to call somebody else, because they're going to need to, because RA has to have changed, because that's how they get back to you. $RA is how they get back to you, so they obviously have to change RA. The V's can change. Why? It's obvious. That's their job to make the change, right? I call a function. I want the answer. The answer is in my V's. So obviously V changes. The A's can change. That might have affected people's peer instruction questions last Monday, because the A's change as well. Can't trust those guys. And the T's can change. You ask yourself, how do I remember this? If it doesn't start with S, it's not saved. Everything else is volatile. Or 0, I guess. Okay? We'll call it 0 from now on with an S. Okay. Anything else? So that's the rules, okay? So what does that mean? What ramifications does it have? It means two things. If function caller calls function callee, think of like main calls foo, then caller must save any temporary register it wants, it needs to use before making the jowl call. Now, if the temporary register is the A and I don't need A anymore, then don't need to save A, because I'm going to call it, that's the transfer of information, that's the call by value. Now you know why it's called by value, right? Because the copy became in A's, it's just a copy. Memory is where the real data lives, and A is just a copy. So I pass call by value to whoever, that can get monged on. If I don't need the A's afterwards, I don't need to save the A's. If I don't need the T's after, I don't need to save the T's. But if you need them after the call, you got to save them before then, because you know that, I promise you, every callee is going to trump on everything. You can't trust it. It's like trusting that the 3 would be the same thing. It's not going to be. So can't trust anything unless you save it. Okay? Callee. What's the callee? Just now I'm in foo. Main calls me. Now I'm in foo. And not to say I don't call anybody myself. So I'm just a pure callee. I'm just the bottom of the call chain. Foo. If I need any, can I clobber an S? Here's a computation. I want to store some data in an S. Can I do that? No, I cannot do it unless I save S first to memory and then work with it, right? That makes sense? Can I immediately write to T without doing any work? Yes. Can I write to any volatile register? Yes. If I'm just the bottom of the call chain, as long as I don't touch the saved guys, the SP or S0 through 7, I can touch anybody. And that's cool. That's fast. And I like that. Okay? So that's it. And again, you don't need to save. People sometimes graduate this, unfortunately, and thinking, oh, okay, so I'm a callee. I need to save, so I'm the caller. I'm going to call somebody. I better save all S's, whether I put something there or not. No, you only save the guys you use, obviously. You don't save all 8 S's for no reason. Don't write to memory if you don't have to. Okay? So, peer instruction. And then, this is cool. We've actually gone a little fast. I get to do some extra slides. I gave you the longest handout in 61C history. And there's never been a case where you had a 4-page handout with slides on every single page. Because there's some bonus stuff that I want to make sure you got, and I'll be able to go into that stuff now. So let's do the peer instruction quickly, and then see if we can do that. And maybe this is too easy, because I kind of said the answer. Ready? Go. I'm caller. I'm going to be reading and writing S0, V0, T0, A0, SP, and RA, and memory. Then the question is, I'm going to push some registers to the stack. I jowl E, the call E, and I'm going to reading and writing, again, the same guys I did before. And then I go back. And now I'm call E, and I'm going to be reading and writing all those guys down there. Okay? What do I need to push in caller before I call E? Okay? I'm reading and writing everything I can in the caller. Then I save some stuff I need to, then call the E by calling jowl E. And then after the call E, I did the same thing. Rewriting all that stuff also. And E reads and writes everything. All according to register conventions, okay? All the legal thing. This is the legal thing. So what does R have to push to the stack before the call to jowl E, which is that guy in green? That make sense? Okay. And here's a list of 6 things, 1 through 5 of those things. One of the few cases where I actually don't mind that there's only 5 choices. By the way, there is a hackathon this Friday, if you didn't know this. Wozniak Lounge, free food. I don't know what that's about, but it's over here. Okay, 180. Come on, let's get to 200, folks. Boy, all these people getting nice sprinkle points at the end of the year. Nice APUF sprinkle points, extra credit for having the clickers and making them use. 300 students, that's like 180. That's like about 80 people who are missing out on a great chance for sprinkle points. Okay. How are we doing here? Ooh, a nice spread. All right, let's stop. Talk to your neighbor. Go. Figure out what the right answer is based on your neighbor's discussion. Let's vote again, and hopefully we'll have better numbers. The numbers weren't so good on the first part, so let's see if we can bring it back to the right space here. Wow. Just about the same. Okay, you're all sitting near people who think like you. The numbers haven't changed. It's pretty funny. Okay, last little bit. Okay. Close it up. Keep voting the last second, and then here's what we got. And it's interesting because of that slide. So S is saved. Those are volatile. So you got to save everybody that's volatile that you've been messing with. So D takes it. Well done, D. Okay. Questions on that? Quite a few people got it wrong. So let's questions. Yeah, stop it. Shh. Go ahead. If I have, the question is, isn't V0 the R returns? It's true. R is going to return that. R may clobber. R may be a void. Who knows? The point is, I had a V0 that I was using based on some other call, and if I'm going to call R, I got to save V0 also, because I know that R is going to clobber it. So if V0 had a value that I wanted later, that's the point. I had data that I wanted later. So if I have that, I got to save it. Yes, question. Shh. If I want to work on them and change them, I don't have to push them before and after the call of JAL E. That's the point of this question. Because I know that E is not allowed to touch my S's. So I had data in S's. I'm going to call JAL E. That data is still there. That's the arrangement that E has with me. So that's the idea. Okay, yes, Christina.
But when you jump to a different function, don't you expect V0 to be changed?
Correct, yeah. If I call it, I expect V0 to be changed. The point of this question was, if I had a V0 that I was working with, and there was data that I needed, then that V is going to be 0, because obviously E is going to clobber it. Yes?
So if you wanted to change S0 and S2, you'd have to store them.
Exactly, that's exactly right. From the point of view of E, if E wants to change anybody of the S's, it has to store them first, change it, and then restore them so that across the JR, it looks like I didn't change them at all. Exactly right. Okay? And there's a really fun analogy that I used to give about lending your keys to a friend. Rather than talk through it, I actually had you read it. So it's actually a slide that I just gave you as a gift of my kind of, you're a friend and you borrow the keys from somebody and you lend your keys for your house to somebody else. I put it in the slide. That's why you have a 4-page handout, because I want to go to actually some real material, and I have 15 minutes. Let's see if I can hit that. So this is the end of the official lecture with there. I haven't taught you logical and shifts, which is what I'm going to do right now. So bonus stuff, I'll go right into there. So there are some times when you want to think of those 32 bits in that register or in memory as 32 independent light switches. Not encoding a word, not encoding an integer, not encoding a float, not encoding 4 characters. Literally 32 separate light switches, 32 separate bits. And these are called bitwise operations. So you may have wondered, if you were a first-time programmer to C or Java, what the difference between 2 ampersands and 1 ampersand is, or 2 OR signs and 1 OR sign. 2 of them means logical, so it just means a 1 or 0. I'm assuming whatever it is, it's a 1 or 0, the output. Bitwise is the word for the single one, and what that does is it treats them all as 32 parallel ORs and 32 parallel ANDs. It's really quite cool, and it's only really used if you want to play with them as bits. So here's an example. Make sure you know this table. This is a table I'm sure you've seen before. A and B is only true when both of them are true. A or B is true with either A or B are true. I don't know if you know that this is a way to look at that table. Who's seen this guy on the right and knows this guy on the right? Raise your hand. Wow. I'm glad I'm showing it to you. It's only like 10 people out of 300. So if here was what A is, listen over here. If A is 0, how does A and B relate to what B is? If A is always 0, how does A and B relate to what B is? It's always 0, right? It doesn't even care what B is. Therefore, if A is 0, A and B is 0. How about if A is 1, how does A and B relate to B? The same. It is B. Do you get that? So what's cool about this is that if I have one input, just B, and the other guy I tie to a switch, if I turn that switch to 0, it ignores B and makes it 0. It's a reset box. If I turn the switch to 1 and make A 1, the switch is A, then A and B becomes a buffer. Just keeps it right through. It's like invisible. It's like it goes away. It's the identity function. Does that make sense? So it is just B. If it's on 1, it just takes B and passes it right through. I ignore you. But if I turn it to 0, then it stops you. It goes, I don't care what B is. Talk to the hand, B, because I'm going to be 0. Make sense? Now, how about A or B? Stay with A or B now. Ready? Watch. It's exactly the same kind of discussion. Look, if A is 0, how does A or B relate to B? It's just B. You see? Look, B is 0, 1, A or B is 0, 1. So it's just B. If A is 1, how does A or B relate to B? Talk to the hand, B. I'm going to set it to 1, right? So now if you use an OR, it's like, put it to 0, it lets it pass through. Put it to 1, it sets it to 1, ignoring what B is. Right? That is so cool. And that's at the heart of what bitwise operations are about. For example, this is just saying that these are all R-type guys. These are logical operations. Here is Z. A bitwise AND is written Z equals X single ampersand Y. Bitwise OR is Z equals X single OR Y. Okay? So watch this. And you have AND and ORs and ANDI and ORIs bitwise. So watch this. Here's 32 bits. Here's my mask with all zeros and all ones here. If I am doing an AND, what is an AND again? Remember, AND is, if it's 0, it resets it. And if it's a 1, it preserves it. So watch. I just, what we call masked out these bits, keeping these guys, resetting the other guys. Isn't that cool? And exactly the opposite thing happens with OR. So I could, is there a thing, is there an F that's missing here? There's an F that's missing here. Oh, no, sorry. This is like the last 3 Fs. That's fine. So this is how you do ANDI right there. T0, T0, OXFF. And that just masks it out. And you can do this thing. We saw this also with Louis ORI. You kind of saw the Louis ORI a little bit, how you can kind of just stuff bits there. So if here is an ORI, and I had OX 1, 2, 3, 4, 5, 6, 7, 8, if I ORI with FFFF, it turns on the lowest bits. So I can either turn them off with an AND, or turn them on with an OR. So I can basically set any bits and turn them off or on independently in one instruction. Okay? That's going to be useful for many, many cases. Questions about this? Yes? No, the ORI and ANDI both are a 1 clock cycle. There's no reason to use ORI versus but the key is you have to use ORI. If you were Louis ORI, why couldn't it be Louis ANDI? Yeah, in the back? Let's go back here. I want to either preserve it or, so Louis ORI, so I'm saying the upper guy is set up, right? The upper 16 is set up. And now I want to set the lower guy, but keep the other guys there. Oh, did you say add I or and? Oh, I see. Add I would be fine, I guess, too. I think add I would be fine, right? Just adding them. Okay? All right. So add is and is no fast. Or and add are all the same speed. 1 clock rate, 1 clock cycle. Nothing's faster than each other, right? Okay? And, or, and add, all the same speed. They're all R-type instructions fast. Yes?
What's the difference between an arithmetic shift and a what shift?
And a what shift?
Yeah, we have an SRA.
Yes, that's here. That's here. That's here. Let me see if I can find it. So you're asking about arithmetic shifts. I actually have that slide here. Shift instructions. Bam. Okay. This is a shift instruction. Shift right by 8 bits, you always fill it with zeros. Okay? Which might take a negative number and make it positive if it's a signed number. So what we use is something called SRA, which is shift right arithmetic, which preserves the sign. So if I have this big negative number, it might be a bigger number or a small number, it keeps it at the same number. It just divides it out. Question?
So the and-I, isn't that going to sign extend? The and-I instead of the or-I, isn't that going to sign extend?
Add-I would. You're right. Add-I would sign extend it. That's right. Add-I-U would work. They both sign extend. You're actually right. They both, that's exactly right. Add-I and add-I-U both sign extend the 16-bit immediate field. That's exactly right. So that's not going to work. That's your question. We have to use or. Yeah, sorry about that. Thank you for the correction, TAs. Oh, there's a question. If you're taking the midterm and you're a DSP student, come talk to my head TA to deal with those issues about what room you're in. Yes, question over there? Okay, so SRA, is that clever? I forget who asked the question, but is SRA cool? I'm jumping around. I want to make sure to cover all these cool slides that we're skipping before. You guys I saw the uses, bitwise. I did this already, right? Didn't I do this already? The mask, I did that already. You've seen Fibonacci already in lab, I think, right? Useful to go over again or not? Who wants to see Fibonacci? 5 people. Okay. So the only part that's interesting about Fibonacci that I saw, all this stuff is pretty easy actually, is the stuff in the middle. Like, you've got this n minus 1, and then you can do this, but you have to save n because you're going to be like doing another call to n minus 2 later. So here's where I save what n is. Then I call, actually this is n minus 1. Then I jow fib. And now fib came back with a v0 there. I now have to reload that into the first guy. So that now a0 has to be n minus 1. And then I make it n minus 2 with this add-I. You can see it there. And now I also have to save the v0. This is what we talked about now. Now this kind of makes sense maybe. Now that you know what the v's and the s's, I have to preserve the results of here somewhere. Where do I save it? As I'm going to call it again for n minus 2 case. Save it to a save register. S0. But what does it mean? I had to have saved S before, because I can't just clobber an S as any subroutine. So if you go back, one of the first things they do is they actually save, I actually save S0. So I give myself one free spot to save a temporary register value. And that, by saving this immediately, means that now I have S0 that I have as a spare space. So if I call fib once, and the v0 comes back, which is the answer to fib of n minus 1, I can store that in my S0 because I know I have that, because I've saved it already. That's the important, that you might not have gotten this back in the days of your lab, but now it makes sense. S0 is now part of things I can save to and trust that it preserves across a call. That's the fin. You notice, by the way, I have to restore S0 also, put it back, because I'm the subroutine. You know, it's this recursion doing that thing, so I'm the caller and the subroutine. So here's where you store the v0 of this guy, n minus 1, into S0. That now makes sense. Now I do a jow fib. See, get it? Place it somewhere. It won't get clobbered, but I just exactly said. Now I say jow fib. Now I know S0's got this guy. V0's got this guy. I just add V0, V0, S0, and there's my return. It's all nice and pretty, and that's the whole thing there. This is the whole thing for that. And there's a closing piece where I have to restore this back pointer, but it's beautiful. This is actually really beautiful if you think about it in terms of how I have one program counter, but I make recursion just somehow work, remembering all this stuff. That's really cool. And key to it is what we learned today, register calling conventions. I know about the S's, I know about the V's. Now I know about it. Now I know why this works. Question? Yes?
Is this just an academic exercise, or is there like some kind of benefit to doing a recursive thing instead of iterative?
This is an academic exercise because if we know about Fibonacci, we know that this is a really bad way to write Fibonacci. So, just like I talked about before, do I always have to store, what did I say, A's and SP if I'm going to do factorial? There are ways to do an iterative factorial. You want to do an iterative Fibonacci. This is like the first exercise, I believe, in 621A. Right? Isn't that the first exercise like thinking about this stuff and how to think of Fibonacci moving it forward in an iterative way rather than a recursive way? Because you can only get to like 27 if you do Fibonacci normally without overflowing, but you can actually, well, that actually has to do with overflow. But anyway, the point is, factorial 27 overflows it, but Fibonacci 27 you can still do, but it just takes forever to do 27. So that's this is how you motivated memoization, and we're in the forward way to do this, all that stuff. That's all 628 stuff. But anyway, this is a cool part to see that C code. This is the kind of thing we ask on an exam, by the way. We say, the easy thing is, here's what I've done a million times. I show you this code, and I say, write the C code for that. And you go, what? And if you would go back, if you can, 2 months, you're like, this is Greek to me. But now it's like, oh, let me see what they're doing. Oh, I get it. They're moving something. Okay, there's 2 jowls. Therefore, there's obviously 2 recursive calls in my thing. I'm starting to build, and then all of a sudden, C code starts to evolve from this MIPS. It's a kind of an easy thing we always do on exams. So think about that. Look at my old exams. You'll see that kind of same pattern. We'll do the same thing this year. Did I cover everything? I covered 48 slides. Are you kidding me? No way. No way. Wait, let me check. No way. Oh, I have my parents leaving for the weekend analogy. Do you want to see that? It's analogy. It's analogy. Okay? I don't know what the PowerPoint problem is. Okay. You can read this. This is fun. You can just read this. I had this whole thing where, okay, now you're the parent and you're the friend and risky bit. It was a fun little act I used to do, but I'll give you guys a break. Leave a couple minutes early. All right. On Friday, Mike takes over. So caches start on Friday. Let's do it. Good stuff.